In this class, I will explain you about one important problem in beams. In strength of materials, we have learned about pure bending of beam. So, pure bending means, I will give an example here. I will consider a simply supported beam AB, which is acted by two equal loads which are equally placed. That means this is, let us say, L by 2, this is L by 4, this is L by 2, this is L by 4. That means you can see that the beam is symmetrical. So it is symmetrically loaded, therefore the reactions are equal. So this reaction will be W, this reaction is also will be W. Now if you plot the bending moment diagram for this, so you will be having a bending moment like this, BME like this. So this value, of course, is subjected to certain bending moment positive. So this bending moment value is WL by 4. So this is WL by 4, and this is also WL by 4. That means between the region CD, in between C and D, you can observe that the bending moment is constant, WL by 4. And if you plot the shear force diagram, so it will be something like this. So at A, shear force is W, then it remains constant, then at C it comes down W like this. Then from C to D there is no shear force. At D you have a shear force of W once again, then constant from B to B, then W here. This is negative, this is positive. That means if you observe, in this region CD, shear force is 0. So bending moment in the region CD is constant, which is equal to WL by 4, whereas shear force is 0. So this state is called as pure bending. That means in the region CD, the beam is subjected to constant bending moment, and also in the region CD, shear force value is 0. So such a case is called as pure bending case. So we say that, so region CD is subjected to pure bending. So pure bending means if a portion of the beam is subjected to constant bending moment and 0 shear force, that portion is called as pure bending, or is also called as simple bending. So only bending moment will be there between C and D. There is no shear force. That is the thing. So in elasticity, we can obtain the pure bending equation. You have learned this pure bending equation in SOM. Pure bending equation is given by M by I is equal to F by V. This is the pure bending equation. So here M is the bending moment, constant bending moment. I is the moment of inertia of the section of the beam with respect to the neutral axis. You know that if you take a rectangular section, centroid will be exactly at the geometrical center, and neutral axis will pass through that centroid. And if you plot the bending stress diagram, so all this you have learned. So it will be maximum at the extreme fiber. It will be 0 at the neutral axis, so F is equal to 0 here. And the nature of bending stress will be, one side it is tension, other side is compression. If it is simply supported beam, the top is subjected to compression bending stress, bottom below the neutral axis is subjected to tensile bending stress. All this we are learned in our strength of materials. So F is the bending stress here, so this is bending stress, and Y is the distance of the fiber from the neutral axis. Distance from neutral axis. Okay, Y is measured like this. So at Y is equal to 0, that means at the neutral axis level there is no bending stress. So there is no strain there. So therefore the diagram will be like this. So compression I can show like this, tension I can show like this. Yes, now let us see how this equation can be derived. M by I is equal to F by Y can be derived by using elasticity principle. So now for that, what we will have to do is we have to assume a stress function, which I have already told Airy stress function, and then we have to find out the stresses sigma x, sigma y, and tau x, y. So this problem becomes a plane stress problem. Pure bending problem will be transformed to a plane stress problem where we have sigma x, sigma y, tau x, y. These three stresses will be having. So if you assume a stress function, so phi is the stress function. Now a third degree polynomial is assumed as a stress function. Third degree polynomial. So you know about first degree, second degree, third degree, fourth degree, fifth degree. So I am going to assume a third degree polynomial for deriving the pure bending equation from the elasticity principle. So the third degree polynomial will be assumed like this, that phi is equal to A3, because I am taking third degree, coefficients, subscripts I am going to take as 3, A3 into x cube by 6. So this is third degree polynomial, plus B3 into 1 power I have to reduce x square, and I have to introduce y there, divided by x square y divided by 2. B3 x square y by divided by 2, plus the third is C3 constant, into I have reduced the power by of x by 1 and I have increased the power of y by 1, xy square by 2, plus d3 into y3. So this is the third degree polynomial, d3 into y3 divided by 6. Okay, this is the third degree polynomial which we have to assume for getting the pure bending equation. Now from the, you have to check whether this satisfies whether it's a Airy stress function. So for that, this condition should be satisfied. Del power 4 phi should be equal to 0. So that is the condition should be satisfied. Del power 4 phi means it is dou power 4 phi by dou x power 4 plus 2 times dou power 4 by dou x square into dou x square dou y square plus dou power 4 phi by dou y power 4. This should be equal to 0. So this is the LHS, this is del operator. So you can check that this phi satisfies this equation because the fourth derivative becomes 0 here. Because the highest power of x is 3, highest power of y is also 3, the fourth derivative becomes 0. So therefore I can say phi satisfies the equation del power 4 phi is equal to 0. Therefore phi is a stress function, it is an Airy stress function. Airy stress function. So once it satisfies the biharmonic equation, so this equation is called as biharmonic. Harmonic equation means it is del square phi is equal to 0. Biharmonic means del power 4 is equal to 0. So phi is an Airy stress function. Once phi is an Airy stress function, you can get the stresses like this. Stresses sigma x is defined as dou square phi by dou y square. Dou square phi by dou y square. If you differentiate twice that phi with respect to y, you are going to get c3x plus d3y. c3x plus d3y. You can do that. Next, sigma y is dou square phi by dou x square. So if you differentiate phi with respect to x twice, you are going to get sigma y as a3x plus b3y. You can check that plus b3y. Then dou xy is defined as minus dou square phi by dou x dou y. That means once we have to differentiate with respect to x, then we have to differentiate with respect to y. So then you are going to get it as minus b3x minus c3y. Minus b3x minus c3y. So these are the stress components we can get that from this function phi. Now we have to evaluate these constants. So there are three constants a3, b3, the four constants a3, b3, c3 and d3. So let us see how they can be evaluated. So for that we have to use the boundary conditions. So you should be very careful now. What are the boundary conditions we have to use? So for understanding condition. Now what I will do here is, I will take the cross section of the beam as a rectangular cross section. Width of the beam I will take it as 2b, and height of the beam, depth of the beam I will take it as 2h. So I will take the x-axis like this, neutral axis. That means the beam runs like this. The beam runs like this. This is the beam, simply supported beam. Now here, let me take this x direction. I am going to take along the length. This is the x direction, and of course this becomes the y direction. Now what we have to do here is, we have to apply the boundary condition. Let me take the length of the beam as L. Length of the beam as L. L is the length of the beam, and origin I am going to take here. It is subjected to a bending moment M like this. So here you can see that this bending moment M is acting like this. M is the bending moment. This is constant. So now what I am doing here is, I am considering this portion. So CD portion I am considering here. This is M. This is also M. It is subjected to pure bending like this. Sagging bending moment I am going to take. Now here what happens? Of course, y direction either you can take above or below also you can take. Now the thing is here. This is H. Total is 2H. This is H. This is H. So using this, we will write the boundary conditions now. So we are going to have three boundary conditions. So first boundary condition is, you have to understand here, at x is equal, at y is equal to plus or minus h, sigma y is 0. At y is equal to plus or minus h, sigma y is 0. That means there is no stress at right angles to the length of the beam. So that is one boundary condition. Second boundary condition is, at y is equal to plus or minus h, there is no shear stress. Tau xy is also 0. There is no shear stress because it is not subjected to shear force. So only it is subjected to pure only bending moment. Therefore the second condition is also okay. Third condition is, at x is equal to any value. You can write at x is equal to any value means from here to here. So from x is 0 here, x is L here. So at x is equal to any value, at x is equal to any value. So what I can write here is, bending moment M is constant. We know that from here to here bending moment is constant. Bending moment, that is M, is constant. Now let us write the expression for bending moment. So bending moment is given by, now we have to understand this expression. Bending moment is given by, so 2b into, I will write the expression, then I will explain. 2b into integral minus h to plus h sigma x into y into dy. This is the expression for bending moment. So you have to understand here. So sigma x is the stress in this direction. Whatever stress is there, that is sigma x. When that is multiplied by, 2b is the, of course, it is the width here. Now what I will do here is, y is measured from this point. So here I will take okay, this is what I am going to take. So this distance I will take it as y, let us say. So then this area of this becomes 2b into y. Please understand here, this 2b into y is nothing but the area above neutral axis. Above the neutral axis. This becomes the neutral axis. So this is the neutral axis, where along with the bending stress is 0. So area above neutral axis is nothing but 2b into y. When that area, of course, is multiplied by sigma x, stress. So you see, this is stress into area gives the force. Because stress is force divided by area. So sigma x into 2b into y is the area. So stress into area gives the force. When this force is multiplied by, once again I write here 2b into y. When this is multiplied by dy, so you are going to get the moment. Dy is nothing but this small strip, this here at this. So this is dy. This thickness is dy. Otherwise you can take like this. 2b into dy. 2b into dy. This I will take it as the area. Yes. 2b into dy into sigma x gives the force. 2b into dy into y gives the moment. Because force is, moment is nothing but force multiplied by distance or revolve around. So this is moment. That is how this expression has been arrived. Since here 2b is constant, it has been taken outside the integral, and y can vary from minus h to plus h. See here. So this y can vary from minus h to plus h. Now here it is y is equal to plus h. Here it is y is equal to minus h. X can take any value. X can take any value from 0 to n. So this is the, so these three are the boundary conditions. So one is sigma y 0, another is tau xy is 0, and third is bending moment constant, bending moment expression. Now using these three, we can evaluate the constants. Now let me number all this. So I will take this as 1, equation 2, equation 3. Here I will take this as 4, this as 5, and this as 6. 6 equations we have got now. Now we have to evaluate the constants A3, B3, C3, all those things, D3. Now let us see how we can evaluate them using the boundary conditions. Now we know that let us use this first boundary condition, that is 4, and apply that to this 2. So we have to combine 2 and 4. So by using 2 and 4, let us see what happens. We will substitute the values now. So applying 4, equation 4, that is applying boundary condition 4 to second, this one. So we will write that first, sigma y is equal to a3x plus b3y. So we have to take y can be plus or minus h. So therefore sigma y is 0. So 0 is equal to a3x plus or minus b3h. So this is what we will get. So here if you see this sum should be 0, means these two coefficients must be 0. a3 and b3 must be 0. Then only it is possible to have this. Because this is a constant. H is a constant, b3h is a constant. So a3x what happens here, x can have any value, therefore the option is a3 and b3, both of them should be 0. Now second I will applying, now tau xy equation will applying boundary condition 5 to 3. So that means here tau xy is equal to minus b3x minus c3y. Once again here tau xy is 0 according to the boundary condition, that is 5. So here this becomes minus b3x plus or minus c3h here also. So once again if you compare, since b3 is 0, c3 also should be 0. So we got all the three zeros. Only d3 is not equal to 0. d3 cannot be 0, because if d3 is 0, then 5 becomes 0. So therefore substituting for a3, b3, c3 as 0 in the expression for 5, then 5 will be equal to, only last term will be remaining, first 3 terms become 0, d3 by 6 into y cube. This is what we get. So 5 is equal to d3 by 6 into y cube. Now once again substitute those things here. So substituting for the constants in 1, 2, 3, in these three. Substituting for the constants in 1, 2, 3. So what you will get, sigma x is equal to so c3x, that means 0, whereas not 0. So d3y, it becomes d3y. Sigma y will be 0 because both a3 and b3 are zeros. Tau xy is also 0 because b3 and c3 are 0. So this is what we get. So only we have sigma x value, sigma y and tau xy, both of them will be zeros. Now I will use the third boundary condition, using boundary condition 6, of course. So third boundary condition is this one, that is equation 6. So m is equal to, I will write m is equal to 2b into integral minus h2 plus h. Now sigma x is there, that for sigma x I can put d3y. Substitute for sigma x as d3y into y dy. Now let us try to simplify this. 2b into, here d3 you can take outside because it is a constant, it can be taken outside. So integral y square dy. So you will get integral y square dy. Between the limits minus 60% y square dy. So y square dy we have to integrate, that means it becomes y cube by 3. So now, we are getting m is equal to, let us see what happens now. M is equal to 2b d3. M is equal to 2b d3 into y cube by 3. So m is equal to 2b d3 into y cube by 3 between the limits minus h to plus h. For y we have to put the minus h and plus h as the upper and lower limits, lower and upper limits. So 2b d3 into this becomes 1 by 3, okay, I can take outside, into h to the power of 3 minus of minus h to the power of 3. So it becomes 2 by 3 bd3 into 2h cube. So it becomes 4h cube by 3 into bd3. 4h cube by 3 into bd3. Okay, so this is what we get. Now let us see d3. What is the value of d3? Let us find out. So therefore d3 is equal to, from this d3 is equal to 3 times m by 4h cube. 3 times m by 4h cube b. This is what we get. d3 is equal to 3m by 4h cube b. Now we will substitute this d3 in this sigma x term 7. Substituting for d3 in equation 7, we get sigma x is equal to d3 is 3m by 4h cube into b into y. Now let us see what is the value of moment of inertia for the rectangular section we have considered for the beam. So this is 2b, this is 2h. So this is rectangular section. If you want the value of moment of inertia about this neutral axis, bd cube by 12. So I is equal to INA, which is b is 2b here into d is 2h here divided by 12. So you will be getting this as 8 into 2 16. 16 bh cube by 12, or it is 4 bh cube by 3. So I is nothing but 4 bh cube by 3. Now here for 4 bh cube by 3, I can write it as I. So sigma x is equal to y divided by this 4 bh cube. That 3 comes right to the denominator of the denominator. So it becomes y by I. So m also is there, of course. This 3 y m will be there here, m will be there here. Now you can write this as m by I is equal to sigma x by y. So this sigma x is nothing but f. So which we have used in pure bending equation. M by I is equal to f by y. This f is nothing but sigma x. So this is the pure bending equation we got in case of a simply supported beam subjected to pure bending or simple bending. So we have arrived at this result using the concept of elasticity, of course the concept of Airy stress function. So we have to assume the third order polynomial as the Airy stress function, find out and check whether that satisfies the biharmonic equation. Yes, it satisfies. Then we have to evaluate those constants A3, B3, C3, D3 using the boundary conditions. There are three boundary conditions here. Sigma y value will be 0, tau xy value will be 0, and bending moment is constant. I have written how to write those expressions. Then substitute those boundary conditions in the expressions of this process and get the constants. And later on, you substitute back only sigma x exists. Sigma y and tau xy they will become 0. So after evaluating this D3, then once again substitute in the expression for sigma x and arrive at the pure bending equation.